I'll start again. Can you hear me? Very good. There is no formal take-home problem in this lecture because there is no recitation tomorrow, so you can't turn it in. But there is a problem mentioned on slide 23, which you should try and at least work it out for yourself. And we will prepare some sort of a sheet so that you can practice the material. But the biggest practice for this lecture is going to come from lab 2. You cannot do lab 2 if you don't understand this lecture. So please pay attention, and you may have lots of questions for which you can go to your recitation instructors and lab assistants and so on. All right. And this is also the final lecture on combinational logic. After that, we will switch to sequential logic, which is extremely important, but we can't understand sequential circuits if we don't understand combinational circuits. So today we are going to look at slightly more complex combinational circuits. And the goal of the lab 2 is to have you design an ALU, which is a very realistic component which is present in just about any computer you can buy, right? So there's a 32-bit ALU you'll be designing, and it's a fantastic exercise. All right, so today's lecture is somewhat about complex circuits, but it's because you already got a glimpse of it from last lecture that Daniel gave. And today you will see how to express such complex circuits in Bluespec. All right, so you have seen this 2-bit ripple carry adder, which we can easily write using, we can express it by combining, half adders and, two full adders in a sort of a cascaded manner. The question comes up, if I want to write a W-wide adder, which adds W bits, then what do I do, right? So in my code, I can't write dot, dot, dot. I mean, that's not going to do, right? So we have to find some other way of doing it. So today's lecture is somewhat about how to generalize this to write a W-bit adder, which means parametrized circuits, where you are parametrizing it first and foremost by the bit width, but there will be many other parameters in these circuits. Okay, so a W-bit ripple carry adder, we cannot write straight line code. So we're going to resort to loops. And this confuses people, because we will have loops, but we'll have no loops in hardware because we are still generating combinational circuits, which are by definition acyclic interconnection of boxes. So we have to understand that, that here is a loop which I'm sure all of you can write, because this is, if you know any programming, this is a pretty straightforward code to write. I have taken a full adder and I'm feeding its output to the next full adder and to the next full adder, and I iterate over it 32 times. And if you do that, you will get some bits out of it, and the final carry bit is the final outcome of this. So if you have W bits, you return W plus 1 bits, from it. So at some level, this looks pretty straightforward, but it's not surprising that most of you find this very confusing. So first question is, how is this different from Python or something, except for some syntactic difference? And I want to clarify all those things. So the question here is, first of all, there are some type errors in this program. It's a kind of an annoyance because you can understand it, but if you fed it to the compiler, it will reject it immediately. But before I get into the types business, because I'm assuming all of you can understand the program that is written here, we need to understand what is the meaning of these loops. When we use loop syntax in combinational circuits to describe combinational circuits, what does it mean? Okay. So first, some preamble, which I do not want you to forget, because periodically you're going to get confused, and we already see some questions on Piazza that tells me that this confusion, at least in some people's mind, is quite common. So never forget that the objective of Bluespec is to describe circuits, right? And circuits, to the first approximation, are like pictures. You're drawing boxes and you're connecting them. You have all kinds of gates, and you're connecting them one way or another, interconnected boxes. But it so happens that these boxes, unlike your PowerPoint, actually have some meaning. So I can tell you exactly what an AND gate means, or what an OR gate means, or some bigger blob. What does it mean? I can describe in truth tables and so on. In other words, they all have some computational meaning. By that I mean, if I give it some inputs, I expect to get certain outputs. Okay? So the boxes, these complex pictures we're going to draw, they have two meanings. You start out with some Bluespec description, and we want to get this complex picture out of it, right? Circuit, where all the things are connected. But we also want to figure out its computational meaning, that if I put two numbers in it, what is the answer that comes out? Because that's how we debug it. That's how we find out whether it's actually doing addition or not, right? And rather than resort to some other things, we just say, we know the meanings of ANDs and ORs, and if we propagate it, we should know what these bits will produce at the output of the circuit. So that's the computational meaning of these things. So the thing that you should never confuse is, even though the primary reason for Bluespec, the only reason Bluespec has been designed is so that you can describe hardware, so that you can synthesize hardware. But a very important aspect of that process is you should also be able to simulate the circuits you're designing, because without that, it will be very hard to debug, right? So this we often refer to as functional correctness. Is it producing the right answers? So these two aspects are tied, and this is where the confusion comes from. So let me illustrate it another way. So I have this 2-bit adder, a ripple carry adder. You give it 2 bits, it produces 3 bits, and we can synthesize it. We feed it to the Bluespec compiler, and out comes this circuit, from it. And you will understand many more details of it as the course goes along, exactly how is hardware being generated, from these descriptions. But the other aspect of this is, any time you write a Bluespec program, you can also simulate it. And when you simulate it, then I say, what is the meaning of add 2 applied to 3 and 1? And it produces an answer. It tells you, oh, you should get 4 in that case, right? So if I feed this, something else, what will I get? You see it in the form of test benches, right? We are feeding inputs to your program, some output comes out, and we check whether your circuit is acting correctly or not. Both aspects are equally important, right? So on the right-hand side, you are getting circuits, which is the raison d'etre for this language to exist. And then for convenience, we also simulate, right? And you should be able to produce the answers that come out of it. So caution, in spite of the fact that Bluespec programs, like programs in software languages, produce outputs given an input, so that part is similar to Python. The reason for the existence of Bluespec program is not the answers you're getting, but the circuit that is being generated. Is this point clear to everyone? Right? Why we are writing in Bluespec and not in Python or some other programming language, other software language? Because we want to generate circuits, right? Because we want to design hardware using this language. Okay, so when we compile Bluespec into hardware, again, you have to keep in mind, Bluespec at some level will just look like a very modern programming language to you. If you're familiar with software languages, on surface, if you don't know what it's about, it's look like any other language. Yeah, it has a plus, bit widths, etc. Add it, something will happen, right? So it's not daunting at all at that level of understanding. But the thing you have to get used to is most of the Bluespec syntax, or what you see in your program, actually gets eliminated during the compile phase. After compiler is done with it, many things that are familiar to you will completely disappear from the next level of representation that is generated, which is much closer to circuits. So for example, all data structures will be converted into bits. So you may use integers in your program. You may use whatever you want. You may use bit 32. You may use Boolean. You may use colors, red, blue, and green. Ultimately, everything is being translated into zeros and ones. And that is being done by the compiler, right? So all data structures are converted into bit vectors. So what about loops? The only meaning of loops in this language is loops are always unfolded. And if you gave me a loop that can't be unfolded, for example, if you have a while condition, some predicate, right, whose convergence is data dependent, well, it's not suitable for describing hardware. Such things will fail, and the compiler will come back and tell you, sorry, can't do it. So any loop you write, by definition, has to be something that can be unfolded at compile time. Okay, so that's very important thing to understand. Functions are the same way. You may have heard that this function calls that function, and stacks and this and that. That's not how functions are going to behave here. Right? Here what happens is you take a function and you say, oh, this function, there is a circuit corresponding to it. So you plop that circuit. In the jargon, it's often called inline substitution. You replace the function body with whatever its body was. Right? So there is no, and this is all being done at compile time. So there is no dynamic calls, no dynamic function calls. Everything is going to happen statically in this. And once you have done all these things, and you may have to do this repeatedly, it takes several steps, then what you end up with is always an acyclic graph of circuits. You know, you will get, what you will get out of it will be acyclic connection of gates or some other operators at the bottom. Now this whole phase is known as static elaboration. And elaboration is a pretty good word here, because sometimes you will write very tiny programs and it can generate a gigantic circuit. Right? So you have to be careful. You know, sometimes it's always good to sit back and ask yourself, how big a circuit am I generating here? You already have a feeling about that from muxes, right? In software, if P, then X or else Y. For us, if X and Y are 64 bits wide, this mux is not a tiny quantity. It's going to take area, right? You have big, you know, lots of gates sitting over there. So you have to develop some intuition about how software constructs translate into hardware, and you know how big they become. Something that may have been free in the software world is not going to be free here, and vice versa. Some things will be free here for which you would have paid, you know, some cost in the software world. Okay. Now, I would like to say, and it could have been like that the Bluespec compiler actually generated circuits directly. But for various reasons, it doesn't do that. It generates another language called Verilog, which is a very, very popular language. In fact, that is the language in which most hardware design is done. So there are lots of tools available which work with Verilog. So Bluespec actually translates it into Verilog, and then we can synthesize from that. You know, we go to gates from that intermediate steps. So there is no intellectual reason to go this way. The only reason is we could have directly gone to gates from Bluespec is a practical one. You know, because if we generate that, I mean, it's the same kind of thing. Why do I compile in Intel assembly code? Because there are lots of processors running Intel assembly code, right? So I don't have to know things below that level. So same thing here. There are lots of tools that we get for free if we choose some standard interface. And for our purposes, you can regard Verilog as some sort of a standard interface. Now, we have gone to great length to ensure you never have to look at Verilog, right? So a lot of effort goes in. So you don't have to learn Verilog. You will never see Verilog in this class. And if for debugging reasons you ever Verilog starts showing up, that means we have failed, right? So really, it's high-level debugging. You will do all your debugging at the Bluespec level. Okay. Now, another problem in understanding circuits is, and this is actually true for any optimizing compiler, even if you compile C, modern compilers can be very aggressive in the optimizations they do. So you write something, and you may not even understand how much optimization is going on behind the scene. So often the circuit, not often, sometimes the circuit that comes out may be unrecognizable. And you will get at least a glimpse of that in lab 2. You will try to understand what happens if I add 2 numbers, what kind of circuit do I get, versus if I design a circuit which takes add, but only adds 4 to it. right? So there is a lot more room for optimization because it's a special purpose circuit, which only adds 4 to things. So you will begin to understand, appreciate these differences. Okay, back to our ripple carry adder. So let's now, with this preamble, see what does it mean to unfold it. I presume intuitively all of you can do it, but let me just make a few points. First of all, obviously I can't unfold it if I don't know the value of W. So this is called synthesis phase. You have to specify what you want. So suppose I said W is 3. So how will the unfolding work? You know, in the very first step, I substitute the value of I to be 0, and I have copied the body. So you see F is being applied to x0 and y0 and c0, and what comes out is c1 and s0. Yes? This is directly corresponding to the body. All I have done is I have put a 0 in place of I. Okay, so I can do the same thing with I equals 1, right? So if I put I equals 1, you will get this. And now what you see in this right away is that this C1 is being fed into the next full adder. So this dependency is automatic. You just write it down, right? And compiler will make sure that these two C1s are the same, right? That's the name of a wire, right? So C1 is connected in this manner. And what will full unfolding will mean? That we also have to go and unfold it once more. So if W was 3, it will unfold this many times. And now you got it. And what can you say about this stuff that you got by unfolding? You may not be able to see it immediately, but it's an acyclic graph. It's an acyclic connection of boxes. There is nothing going back in this, right? All the arrows are going forward in this. So, you know, I've just written the same thing here in a more compressed form so that I have space. Another way for me to draw this would be that unfolded loop defines an acyclic wiring diagram. And this is what you saw, that full adder has x0, y0 going into it, and you're feeding the carry in and carry out from it, and everybody produces a sum bit also. And the way this is a made up notation that actually what F is producing at any stage is 2 bits. So I just drew this arc, and you know, one bit I'm calling C2 and the other bit I'm calling S1. Is this clear? Right? So this is just, you know, software hardware interaction, but there is no operation. There were 2 wires coming out. I refer to them as CS0 in my program, but one of them, when I select it, is connected to the next full adder, and the other one goes out as the sum bit. Good. Each instance of function FA is replaced in its body. So now I can go and say, what do you mean by FA? It's a function call, right? One and only one meaning. Go and take the circuit corresponding to full adder and put it in here. So you have, if you thought this was big, it's actually bigger, because now you have to replace each FA by the corresponding gates that correspond to it. And it's absolutely cut and splice. You can take out this box F of A and plop, you know, the circuit corresponding to F of A, and it's guaranteed to meet at the boundaries. No mismatch is possible if it's a type correct program. Okay, so is this much clear to everyone? That any time I write loop in Bluespec, and there is no exception to this, any time I write a loop, it's always unfolded at compile time. Yes?
So if we make function calls inside a loop, that either creates a circuit or by cycles uses a circuit already created, right?
Right.
What about variables?
What about variables? Yes,
So
good.
I see that we came up with a naming convention here, CS0, CS1.
Oh, yes, yes, yes. So compiler chooses some naming convention.
Is it possible for the compiler to choose a naming convention such that before
No, no, no. It will not make a mistake. I thought you were going to ask a harder question. The compiler convention is such that you may have no clue which wire it's referring to. Right? So even though compiler has a systematic way of doing this, but that doesn't mean that naming convention matches our intuition. So whenever you do this elaboration, sometimes it's very, very hard even to find inputs and outputs. Internal wires, no chance, because there'll be optimizations. If you're looking for CS0, it may be very hard to find it in the circuit. Yes?
What if W can change? If W can change from or can W change?
You're asking a very, very good question. So this is a big, big difference between hardware and software, right? In software, when you write a parameterized program, just give me a new value of W. We are happy, right? We will execute it for that case. Not in hardware. 32-bit adder is fundamentally different from a 3-bit adder. Right? So actually, that's the next slide. I'm showing you that given this parametric adder, suppose I want to make a 3-bit adder. Right? So how do I define it? Right? So this is my general adder, and now I want to define a 3-bit adder. All I have to do is write this. I can just reuse the circuit I have already defined. Add n. So this may be slightly confusing that all I wrote here was this. I didn't specify anything about the size of x, y, and c0. So how does the compiler decide what is the size of it? How does it know that you are trying to build a 3-bit adder?
So add n is parameterized by W. So if you give it an x and or a y, it'll check how many bits it has, and using that assign the value to W.
No. Okay, good try. Anybody else? How do you know? Yes. Sorry, say that again? Recursion. You can also write recursion, yes. And same rules apply. Recursion must terminate at compile time. Right? So it must be very, very finite and cannot depend on any dynamic values. And you will keep substituting the procedure. So you'll just keep unfolding it. But before we go to recursion, yep.
Does it look at what you're trying to output and return W from that?
Exactly. So it looks at left-hand side and right-hand side. And it says, aha, you are telling me x is 3 bits. So I'm going to assume x is 3 bits. So it's instantiating based on the output you're demanding. You're saying, I want a circuit, which returns 3 bits, and I'm going to feed it x and y, which are 3 bits long. So compiler knows all that. It looks at this and it says, aha, that's what you meant, right? That's what you must have meant. And if it can't decide all this, it'll say, sorry, I can't figure out what you're trying to say. Yep.
How is that different from what you said?
I thought he meant dynamically you can quiz how big is x and y. You can never quiz, right? It's declared. It's declared here that, this x is 3 bits wide. Therefore, this x also must be 3-bit wide, right? You cannot, there is no possibility in hardware or even in software to actually ask the question, how big is x? It's like instantiation of variables, right, in this. Should I move ahead? Right, yep.
I didn't get to the discussion about if I can make a change in this variable that's
So which variable will you change? Now tell me.
for I smaller than W.
Uh-huh.
W inside the loop.
Oh, you can always go and rewrite that function and substitute the W yourself, right? That's completely different. So we are not even looking at what is inside that circuit. All we know is type says that it accepts values of size W and returns an answer of size W plus 1, right? That's all we know about the function. But you are not allowed to write anywhere that the value of W is 3 explicitly when you call it. Yes?
You have to wrap add 3 in a function that calls
I think you can do that also. You can directly write it in the call itself, the value, and that will work. But I think the reason you do it like that is because you want to use add3 from now on, right? So you will see this theme emerging all the time that when you start instantiating, you want everything to be of the same size. And it's very, very annoying to keep writing 3, 3, 3 everywhere, because sometimes by mistake you say, oops, this was supposed to be 2, right? Or this was supposed to be 4. You're avoiding all that problem by writing in this manner. Yes?
If you all had n instead of add3 in a bunch of different places, would it create that same circuit in a bunch of different places? Or would it create it once and then just use
Very good point. So I will come to that also. Sometime you're asking if it sees the same circuit, does it try to use the same one? You know, what is in compiler jargon is known as common subexpression elimination. You know, so there is enough known about this that we can take two things and recognize, oh, these are the same expressions. Perhaps we could have shared the same circuit. Advanced topic. Maybe I'll come to that in this lecture later on. Okay. So, I already said all this. Numeric type W on the right-hand side implicitly gets instantiated to 3 because of the way you wrote the code. And similarly, you could have done, you know, a 32-bit thing. You could have defined a 32-bit adder, and the right-hand side remains the same. So the use of parameterized circuits is all the time. You write it once and use it many, many times in different situations. I like to think of this as we are instantiating the add circuit for 3 bits and for 32 bits and so on. And instantiation is much, much simpler than rewriting the circuit every time. There is a lot more room for mistakes in that. Okay, so now enough questions are coming about types. Let's fix our program so that it actually runs. So what is a type? At a very, very simple level, type is simply a grouping of values. You know, so when I say bit 16, I mean anything that has 16 bits is bit 16. You know, we're just going to call it all numbers on all bit patterns which fit in 16, bit 16, right? That's the group. That's the set, if you want. It represents all those values. We have given it a name. We are calling it bit 16. Okay, bit 15 to 0, this is an exception. You can ignore it. You never have to use it. But this is this is also allowed. Now, look at bool, right? So bool it's a 1-bit value which represents either true or false. And when you use bool, the system will not let you substitute 1 or 0 for it. Because as far as the system is concerned, it's a bool. It's true or false. You can say, I know, but true bool is 1. No, sorry. In this system, bool is bool and bit 1, which can be either 1 or 0, different entities. You cannot mix these two different types. Okay. Unsigned integer, 32. So you are saying 32 bits which represent an integer. All right? Vectors of 16 elements where each element itself is an int of size 8. Make sense? Yep.
Vector somewhat like a software list here?
I think so. No, I mean it's not a list. It's really a vector. It's always fixed size, right? So you have declared the type to be 16 in this, and you can select from it, and you'll be able to assign to it. But you can't think of it in terms of software vector. It's just a naming convenience. So vector is, you had lots of things to name, and instead of giving them 16 different names, we'll call it x, and then I can refer to x0, x1, x2. Whenever I refer to x1, x0, I mean that int 8, right? So it's only a naming device, Yes?
What would you use a vector
That let's wait, because there are so many types. I'm just giving you minimal stuff, and they will naturally arise, for you to use. I'm not giving you a comprehensive lecture on types. Yes? Sorry, say that again? So what do you do to ints? What operations are performed on ints? Add, subtract. We don't do that with bits. We can, if we want. I mean, we can get into the representation of how an int is represented, right? So this is very important. Whenever I think of a type has associated operations with it, right? So when I say bool, you think of true and false. What do you do with true and false? You can do a logical AND, you can do a logical OR, you can do a negation, etc. Right? You can only perform those kinds of functions on a logical variable, nothing else. If you write, bool 1 plus bool 2, that's an absurd idea, right? Because we don't add bools, we do ANDs or logical operations on that. Okay, yes?
Are these all describing something in the circuit, or are any of these talking to the compiler?
Everything will talk through the compiler. So this is now, for a moment, I'm saying forget about circuits. I will relate it to circuits. This is, I'm describing you the properties of the language, right? So in language, a Boolean is different from bit 1, right? And int 32 is different from a 32-bit number. I mean 32-bit, arbitrary 32-bit quantity, right? Of course, everything has to be represented in terms of bits ultimately. Yes? Sorry, say that again?
Does it mean 16 8-bit integers or 2 8-bit integers?
No, 16 8-bit. So this is, the first thing is telling you how many elements are there in the vector. And then each element is 8 bits. 8-bit is just a short way of saying it's an 8-bit bit vector, right? It's used so often that we have special syntax, bit number sign 8. Yep.
But does the circuit has any kind of differentiation? Like, is there anywhere in the circuit where it's defined that this thing must receive a bool and this thing must receive a bit? Like, if there's any memory?
So it depends at what level you are asking this question. At the Bluespec level, absolutely. If it's expecting a bool, you give it 1 or 0, it's going to fail. Compiler will tell you, sorry, you're trying to confuse me. This is the Boolean, you're giving me a 1, which is not a bool, right? At the circuit level, everything is going to become 1s and 0s. That's the role of the compiler, how it takes all these data structures and converts them, how it takes everything and converts them into 1s and 0s. Yep.
If I get a gap, that's if you receive an integer, and then, I don't know, I'm trying to put an array of bits in it. Like, this circuit has no place where it checks whether that thing is represented.
Yeah, you should not even think that I'm storing it anywhere. So if I say x is vector so and so, all I've done is I've given it a name, right? You should not think that these are storage cells or anything. They're just wires at this point, right? You have something and each wire is, so if you go down to some level of detail in this, vector of 16, 8 will ultimately result in 8 times 16 wires. And I have just given you a way of numbering them, right? So if you go to number 2, so you're looking at that group of wires which are numbered 0, 1, 2, 3, 4, right? Very good. Okay, so every expression in Bluespec program has a type. So no selectivity in this. Every expression, no exceptions to this, every expression has a type, okay? Now sometimes you will write down this type explicitly, and sometimes compiler is smart enough to figure it out. And we actually rely on this compiler smartness, that let it deduce some types, otherwise it will get too tedious. You'll be writing so many types in your program that you'll get bored. It's not difficult, it's just tedious. So this automatic derivation of types is very, very important. Basically what program compiler does is all the time it's checking the type things you have specified explicitly, are they consistent with each other? And if they are not consistent with each other, then it says, sorry, your program is incorrect, type incorrect. Okay. So yeah, in the jargon we often say an expression has a type. Or if you want, we can say an expression belongs to a type. Right? Why do I say it belongs to a type? Because remember, a type represents a set of values. So what you are saying is that when you evaluate this expression, it's guaranteed that its value is going to be picked from this set. So both these, this is just a way of saying, and you will get used to it, and they are just equivalent to each other. The last thing is that compiler assigns a bit representation to every typed value that is implementable in hardware. So there will be things we talk about in terms of types which have nothing to do with hardware. They're just programming convenience. But anything that eventually shows up in hardware, compiler is going to translate it into a bit pattern. Yes? I'm coming to that. Okay. Very good. So now, if you ever wanted to see what's happening with these types, you actually can't look at it directly, but these are the two functions that are used. So whenever you use pack, it converts a bit pattern into the desired type. So I can take 32-bit, a pattern of 32 bits, and I can say, please convert it into a 32-bit unsigned integer. Or I can go the other way. I can give it a data structure, a number, a Boolean, whatever, and I say, unpack, can you please tell me what is the bit representation corresponding to it? Okay, so these are the two functions, and my hope is you never have to use them. Once in a rare bit, you may have to use, pack and unpack, but anytime you have to use it, use it with caution or ask somebody, do I really have to use it? Or was there another way of writing this so that I did not have to look at the bit pattern at all? Okay. Now, yep.
When you run pack or unpack, does that mean anything on the circuit, or is that?
No. It's completely a compile time thing. It's just way of going from this high-level fancy language, Bluespec, saying, tell me how do you represent this number? What is the packing of it, right? So you can look at it in the unpacked form, which is the bit pattern, and vice versa. And it's unique, right? So there is no two ways about it, right? So, okay, so I have already been using this number sign all the place, but this is, any time you see this in a type definition, it means it's a parametrized type. That means, oh, I can build more interesting types by substituting a value for a variable in there. So look at the example. So I write bit n. Well, what that means is that you can substitute any integer for n. So you can write 1, 32, 8, etc. And that's instantiating that type to a very specific type, right? So given bit n, you can make it into bit 1 or bit 32, etc. Here is a slightly more interesting example. So here is a 2 tuple, right? It has two components, and both the components are integers in this. Now, integers are a very strange beast because they are unbounded in Bluespec, so there is no hardware representation. They will just be a programming convenience whenever we use integers. When we use for computing, then we will use ints, and we always specify the bit pattern, not bit pattern, bit size of it. So somebody asked about functions. So how do I read this as a type? So you have some function name, fname, and I'm saying its argument is integer, and the result it returns is an integer. So I said every type describes a set. What set is being described here? Sorry? Set of all functions which map integers to integers. Right? So I mean, mathematically, if you are thinking, there is a set which may be tremendously large, I don't care. But you have constrained it. If you are expecting a function of this type and somebody try to feed it, a Boolean, it will immediately say, sorry, not, you have violated the types. So when I say things have types, everything in Bluespec is going to have a type. Right? Functions have type, modules have types, everything is going to have types. Okay. This is just to avoid mistakes. Normally I don't discuss such things in the lecture, but you should get used to it. So all type names must begin with a cap letter. Okay, so that's why I write capital B. If you wrote small b, it won't work. Capital bit, number sign, int, integer. Every new type that you will define must begin with a capital letter. Yes? Say that again? If the function is expecting that type, yes, you'll see examples of that. You can pass functions to other functions as arguments, but I won't go that far yet. So anytime you have questions about types, just try it. I mean, you'll be amazed how many things will work, right, in this regard. Okay, a type variable is always written with a small letter. So this is a very big distinction, and in the beginning, if you're not used to it, you get confused by it. All right. So type synonyms is another thing which we define very liberally. So I write type def bit 8 because I use it so often. I call it a byte. Remember, byte is written in capital because it's another type being defined, right? Word, I can call 30, and this is up to me. There's nothing built in. I can define it any way I want, right? Tuple. So here is a pair. What does this say? Why am I writing pair? Because it has only one type parameter A, because I'm saying both the elements of this tuple are of the same type, which is type A. Yes? Sorry? It's defining a new type. It's defining a byte. It's defining a word. Yeah. So from now on in your program, you will be able to say something is a byte. What is its type? Byte. So types are built on top of each other, right? And you will find with every program there is a gigantic type file that sits in the beginning. And you have to often import that file where all the types have been defined. Yep. Sorry, say that again. There will be problems. No, sorry. There will be no problem. If you use type def, it's a synonym. So it's like you can substitute it either way. Okay. Data size. This one was interesting. So you see, data size is a numeric type. Right? I'm saying it's 32. So 32 is also a type, right? Because I'm using it for defining types. I think I'm running out of time, so I'm going to speed up slightly over here. Oh yes, this is very important. Enumerated types. So this is the best thing since sliced bread. So once you start using enumerated types, you say, man, I should have always used them. Let's take a very simple example, color. Right? So suppose you're expressing something and it has 3 colors. So you could have done your own encoding. You say every time I write 0, 0, it means red, and 0, 1 means blue, and 1, 0 means green, right? And there is no difficulty. You can write your program that way. But a modern way of writing this would be to define a new type. And that new type is color. So I've defined a type color. And it's enumerated types. You say color can only be three things, red, blue, or green. Okay, for a moment, ignore this deriving thing. So do you understand what type def says here? It's very clear, right? I'm defining a new type called color, and at least according to my definition, there are only three colors. Now, we know that anything you write, anything you define, there has to be a bit pattern associated with it, which you could have given me yourself. You could have said, oh, whenever I write red, I mean 0, 0. I strongly discourage you from doing that. I'm not even going to tell you how that is done. So when you say deriving, system is picking for you a bit pattern for this. And if you open up the reference manual, it'll actually tell you exactly what bit pattern it'll pick. It's deterministic, right? Yes?
Wait, so, sorry, can you repeat? What do enum and deriving do?
Sorry?
What do the keywords enum and deriving?
So enum is a type, right? So just like you had bits, you have enum here. And now what we have constructed, this new type we are calling color in this. So just compare it to the previous slides, right, where I was doing type def, I was giving something and giving it a name. Name I'm giving it is color in this case. Now, yeah.
Why isn't enum capitalized?
That's a very good question, and I was thinking of that too. And I think this may be one of the few exceptions. So I think because bit was another exception, and Daniel pointed out int is also an exception. Okay, I'll reply to this question on Piazza. All right. Now, another thing you will discover is any time you define a type, you are immediately getting into, oh, how do I compare two colors? Right? You know, because now I write a program and I say, is this color equal to that? So now you'll have to give me a definition. Red equals red. Red does not equal green. Right? So you could write such a function. Very boring, trivial and boring. So you can say, please derive the equality for me. Compiler will derive the equality for you. So this will become a refrain for you. Anytime you define types, you will see deriving, bits and EQ. That means it's deriving the bit pattern for you, and it's deriving the equality function. In fact, there will be many other such things that will show up, which compiler can automatically derive for you. Okay, Bluespec compiler automatically assigns a bit representation to the three colors. So the question comes up, why is this better? Why is this style of coding better than you yourself coding and saying red is 0, 0? Anybody? Yes?
Abstracts the encoding in represent
Right. So?
You don't have to worry about the abstraction part.
Well, yes, but there is even a more important reason. We do not want to confuse the color with 0, 0, which you may have used for something else. It may have been a number, it may have been something else. Something else is represented with 0, 0, right? So if you are working with bits all the time, you don't get that safety. The moment you work with enumerated types, you can compare colors only with colors. You cannot compare color with temperature, because it will be a type failure at that point. So really, types prevent us from mixing colors with raw bits. And you have already seen this type declaration versus type deduction. So the main sledgehammer you have is to use lets. Anytime you use let in your program, that means it's deriving the type for you. And you type this in and it will come back and complain, type error. What is the type error here? Right, so I gave it away by writing it in red. Right, that's the error. right? It's not 2 bits, that thing. So, compiler will figure it out. It looks at it and say, something is wrong here, type error. Sometimes it will even give you a meaningful message, pointing out where exactly the type error is. So, we are over time. Can I go? Okay, guys, I want to take 2-3 more minutes. So please, because this thing is, we have given you enough background for you to understand this. Okay. So the thing that was wrong with this is that I wrote W plus 1, right? There is, whenever I write W plus 1 like this, it's not allowed. Why it's not allowed? So I think the thing you have to understand is there is the types world and there is the value world. What is the types world? It's always naming a set. This set of value is called something. And values are specific instances of it. So what does it mean to take name of a set and say plus 1? That doesn't make any sense, right? But it turns out that there are times when, especially with numeric types, you say, I mean one more, right? But you have to understand W comes from a different universe than the value, right? Value world, it's not a value, it's a type which is 32. So anytime you want to cross this world, you will have to write something like value of. So if I write I less than W, it's not type correct. Why? Because W came from the types world. Remember, I had used it for specifying how big my numbers were, how big my input was in this case. So you can always extract the value of a numeric type by writing value of. So the moment you write value of W, now you are down to the value world, and then it's absolutely fine to compare I and W. So once in a while you will see this, that the other thing is we can't do W plus 1 because that's an operation in the value world, right? I'm adding 1 to something which you all understand, but it doesn't make sense to add 1 to the name of a set, right? So 32, 16, what does it mean? So we use a different language for deriving such names, and that's, you will use this type add, right, W comma 1 instead of writing W plus 1. So only 3 operators are defined in the types world. For doing arithmetic, one is type add, type multiply, and you also have type logarithm to the base 2 is also allowed. So if I write bit W plus 1, it's not correct. And if I write bit tad blah 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 W comma 1, then that you're getting 1 more. So to make that program correct, all I have done is I have replaced W plus 1 with T add, and I have replaced W here with value of. If you make these 2 changes, then this program becomes type correct. Previously, we were mixing types world and the other world, which you can't do. So, okay, I'll stop here. Thank you.